Challenging geometry question to finish this Hamilton Olympiad. Where to begin to try and prove that these three bisectors, two angle bisectors and a perpendicular bisector show that they must necessarily meet at a point as indicated. Well, we're told in this quadrilateral that AB plus CD is equal to BC. So that is going to be a crucial piece of information. The fact is not going to always be true, but it's going to be true for this particular quadrilateral. So it took me a little while to get my head around how to use this, but actually what we can do then is basically split BC up. So if I know that AB plus DC is BC, then I can draw in a part that is the same length as AB, and then the remaining part is going to be the same as DC. We must be able to do that. And what this does is create equal lengths here and here. And if we connect them, then we create two isosceles triangles. Now, a consequence of this is that these two angles will be the same, and these two will be the same. But in fact, the most important thing is that actually the red triangle, because we've got angle bisectors, that means that this is going halfway down the triangle and we're going to get right angles. That is a right angle, that is a right angle, and here as well. And this brings in an idea, and it takes, you have to kind of spot it, but we actually have to focus now on this triangle here. So consider triangle A, D, I'm going to call this point X. So ADX. Now we have, I'm going to label it L1. So L1 is a perpendicular bisector of A and D. L2 is a perpendicular bisector of D and X. We'll write the whole thing out. And then finally, if I call this one L3, then it's a perpendicular bisector of A and X, or AX, the line. So I've managed to turn this problem from two angle bisectors into having three perpendicular bisectors. And there's something crucial about this. So L1 is the set of points equidistant. See, when you draw a perpendicular bisector, you actually create a locus, a set of points the same distance away from A and D, in this case for L1. L2 is going to be the same stuff, but from D and X. And then L3 from A and X. And therefore, there will be a point equidistant from A, D, and X that all the perpendicular bisectors go through. So for example, L1 is a set of points halfway between, well, equidistant from A and D. But because L2 is equidistant from X and D, now if we find out where um, those two cross, then that will tell you where the point is the same distance from A, D, and X. And if you bring in L3 as well, then it's going to cross in exactly the same place. So that is enough. There'll be a point equidistant from A, D, and X that all the perpendicular bisectors go through, and therefore the lines L1, L2, and L3, which are the bisectors shown, will cross at the same point. And that's all we need to do. So once you understand this question and implement that triangle and realize that fact, it's not too bad. But obviously challenge one is understanding how to use this piece of information to create these isosceles triangles. And then challenge two is like, what is the consequence of that? And you have to spot that now we have three perpendicular bisectors and the property of it. Just finally, one nice property of this is that because we found the point that is the same distance away from A, D, and X, then if you were to get your compass out and set the radius as, say, A, then if you draw a circle, it's necessarily going to go through D and X, and you actually create a nice circle that will look like that. Okay, well done on your efforts on this question, and thanks for watching. Well done on the whole challenge.